What's going on, guys? In this video we're going to be covering different resampling techniques and the feature selection method of subset selection. So why use different resampling methods? So because data is often limited, either because it's expensive or there's not enough data collected on a certain subject, we use resampling methods. So what resampling methods allow us to do is achieve better accuracy with limited data, as well as make better predictions of what our true test results are going to look like. The first resampling method we'll talk about is the validation set approach. So what the validation set approach does is it divides our data into two parts. We have the train part and we have the validation part. So observations will be randomly assigned to one of the two groups. So we'll say the first 4 observations are assigned to our train data. And we'll say the last 2 are assigned to our validation set. So what will happen is we'll train a model on our train data, which will be about 60 to 80% of our data, and then we'll be able to test that model on our validation set, which will be about 20 to 40% of the data. So what this allows us to do is it gives us the ability to test the results of our model on data that it hasn't seen yet, or a validation set. So this will give fair estimations of what the true test mean squared error will look like. Now the problem with this is we're only using about 60 to 80% of our data to train the model. So because we're only using a small subsection of our data, we're going to have high bias. And as we learned in the variance bias trade-off, this means we'll have low variance. So this is the simplest of the methods. The second method we'll talk about is cross-validation. So the first step in cross-validation is to assign k a value. So what k does is it will divide our data into that many equal parts. So if we use k is equal to 3, we're going to divide our data into 3 equal parts. So we'll do that now. So this will be part 1, part 2, and part 3. So we'll add our first 2 observations to part 1, our next 2 to part 2, and then our final 2 to part 3. So our cross-validation has 3 parts, so it's going to have 3 iterations. So at each iteration, what it's going to do is it's going to train a model on 2 of the parts, and then it's going to test the model on the 3rd part. So in step 1, it's going to train on the first 4 observations, and then it's going to test our model on the last 2 observations. And then say we're using linear regression, it'll get a mean squared error. So let's say the mean squared error from building a model on these 4 observations and testing it on these 2, and let's say we get 20. So now it's going to still keep the same 2 parts, but it's going to train on a different 2 groups, and it's going to test on the second group. So now it's going to train on groups 1 and 3, and it's going to test on group 2. So the observations will stay the same. So it's going to build a model based on these 4 observations. It'll test on these 2, and say we get a mean squared error of 30. And then the final possibility, it's going to test on this first group of 2 observations, and it's going to train the model on these bottom 2. So observations are in the same place. And then we can say we get a mean squared error of 40. So the final result it's going to produce is going to be the average of the results of all 3. So it's going to say the mean squared error is going to be equal to our 20 plus 30 plus 40 over 3, which is just going to be equal to 30. So this is going to be the predicted outcome. So this k value we chose a k value equal to 3. So as our k value decreases, the bias will decrease, which means as our k value increases, our bias will increase. Now if we were to drop our k all the way to k is equal to 1, this becomes a special case known as leave one out cross-validation. So leave one out cross-validation is a special case of cross-validation where k is equal to 1. So what this means is that we're going to train on all observations but one in the data set and then test on that observation and then repeat this process for each observation. So we'll follow the same trend that we did for cross-validation. We're going to train on our first 3 observations and then test on the 4th one. So observation 1 is 1, 2, 3, 4, 4, 6, 5, 8. And in the next iteration, we're going to build a model based on observations 1, 2, and 4. And then we'll test on observation 3. So 1, 2, 3, 4, 4, 6 we'll test on, 5, 8. And then we'll do this 2 more times until we test on each of the observations. And then we'll take these results and we'll average them together, and that will be our cross-validation mean squared error. So it would just be the mean squared error that we got for the first one, or training on these 3, tested on this one, plus the mean squared error we got training on these 3, tested on this one, and then so on for the other 2. Okay, so now if we compare the 3 models we learned so far, or the 3 different sampling methods we learned so far. So the validation set approach. So since we only use such a small amount of observations, this has the highest bias of the 3. But it has the lowest variance. Now cross-validation, we have somewhat of a midway point for the bias and the variance. And then the leave one out cross-validation, or just saying k equal to 1 in cross-validation, we have the lowest bias and the highest variance. So which one's better? So generally you're going to use cross-validation, and you're going to set k is equal to 5 or 10. So this is like somewhere of a midpoint, and it generally provides the best results. Okay, now problems with leave one out cross-validation. So leave one out cross-validation essentially checks every observation to a different model. So say you had 10,000 observations. So it's going to build 10,000 models. And then run those models against one observation at a time. So as you can guess, runtime starts to become an error and computation costs. So for large data sets, you cannot use leave one out cross-validation. Meanwhile, if we were to use just cross-validation of say k is equal to 10, even if we had 10,000 observations, it would only build 10 models. And then for just validation, would have the quickest runtime, where it would only build 1 model, even if we had 10,000 observations. So last section we covered k and n, but we never learned to choose the appropriate value of k. So with cross-validation, you're able to achieve this. So the way this would work is you'd ultimately enter in different values of k, say 1 to 20. And then you would run cross-validation for each value of k. So for k is equal to 1, say you run your 10-fold cross-validation. For k is equal to 2, you run your 10-fold cross-validation. And you do this all the way till k is equal to 20. So for each of these guesses of k, you're ultimately going to run 10 models using the 10-fold cross validation, and then you're going to take the average of those models. So you're going to end up with mean squared error 1, mean squared error 2, all the way to mean squared error 20. So whichever mean squared error produces the best results, or has the smallest mean squared error, so say it was mean squared error 10, you'd ultimately choose this model and assign your value of k to 10. So you could say that with a k value of 10, you'll achieve the best test results. And that's done using cross-validation. Bagging. So we're only going to cover this one briefly, but essentially how it works is you start off with your original data set. So here we have 4 observations. And then it's going to build new data sets that are pretty similar but slightly different. So how it does this is it chooses observations at random, but it can choose observations more than once. So let's say it chooses observation 1, observation 2, observation 3, and then it chooses observation 3 again. So if you notice, observation 4 is not included in this one. And then you can do the same thing again. So it might choose observation 1, observation 1 again, and then observation 3, observation 4. So it can do this hundreds, if not thousands of times. And then what you'll end up with is a bunch of tables that are slightly different. So the main goal of doing this is to lower the variance. So we'll learn about this when we start talking about decision trees. Is basically when you combine a bunch of trees, instead of just having one tree, you'll have a lower variance. So the math, there's only one math you have to learn for this section of bagging, which is essentially 1 minus 1 over n to the n. And this is just the probability an observation won't be chosen. So here, if we look at the first table, observation 4 wasn't chosen. So the probability that we don't pick 4 is just 1 minus 1 over 4, because there's 4 observations to the 4th. Or just 0.75 to the 4th. Now this number is always going to be somewhat near 1/3. Now we can talk about feature selection. So we learned last section that we could drop predictors from our linear regression model if they're not significant. What happens per se if we had hundreds of predictors, or in this case we'll just say 100. So if we're using a 5% level of significance, ultimately what's going to end up is we're going to have 5 predictors in our model that have nothing to do with our dependent variable. So now we're going to learn better methods where we can ultimately limit the number of predictors we have and create the best test mean squared error possible. So over on the left, we have different outcomes from our full model, which would be y is equal to beta 0 x1 plus beta 2 x2 plus beta 3 x3. So on the left, we have every possible combination that we can form from these 3 predictors. So here would just be the intercept, here would be our beta 0 plus beta 1 x1, then the last one would be our full model. So our goal is to choose, using best subset, is to choose the best model for each count of predictors. So for instance, if we have no predictors, which is just our null model, we don't have a choice, we'll just pick this model. Now if we're going to add only one predictor, then we would choose this model because it's the lowest sum of squared errors. Now if we're to add 2 predictors, what's the best combination? It's just going to be this model because it has lowest sum of squared error. And then if we're to add all predictors, we don't have a choice, it would just be this model. So writing that out, we would say our best model for 0 predictors just has a sum of squared error equal to 180. And then our best model with one predictor has a sum of squared error equal to 100, and that'll be using predictor x1. And then our model with two predictors, we would use x2 and x3, and we get a sum of squared error equal to 50. And then for our final model, or three predictors, we would include x1, x2, and x3, and we get a sum of squared error equal to 40. So now we narrowed down all possible predictors, and we ended up creating 4 possible choices. So the best model with no predictors, the best model with one predictor, 2 predictor, 3 predictor. So now how we ultimately choose which is going to be our final model is either we can use cross-validation, like we learned before, or we can use some test statistic that has some type of weighted mechanism for added parameters. So for instance, you couldn't use r squared here because we learned that as you add more predictors, r squared will always increase. But we'll learn that there are 4 statistics we can use where they have a weighted mechanism, so as you add predictors, the results don't always get better. And we're going to learn that at the end of this video. So we just learned best subset. Now we're going to learn forward selection. So why do we need different choices? Why can't we just use best subset for everything? Well, here's the problem with best subset. So because we're checking every single possible combination, we're going to end up with 2 to the p, or the number of predictors, different models built. So for each time it'll test a different predictor, it'll build a model, and it'll get the sum of squared errors. So there we had 2 predictors, so we're only going to end up with 8 models. Let's say we had 30 predictors, then this number can get really big really fast. So the problem with best subset is you can't use it when you have a lot of predictors. So you can't use with a lot of predictors. And the second problem is, because you're ultimately trying every possible combination, so just like when we wanted to reject our predictors when we had, say, 100 predictors, ultimately you're going to end up with, on average, 5 mess-ups. Well, the same thing happens with best subset. When you're ultimately trying every single possible combination, you ultimately find a combination that could look good, but really won't perform well on the test set. So you're essentially, a fancy word for that is data dredging, where you're just trying every single possible combination until you get something that looks good. So now we can introduce forward selection. So forward selection works is we're still going to start from no predictors, and we're going to add predictors one at a time. So we're still going to include our null model, or no predictors. We'll have a sum of squared error equal to 180. And then if we were to include one predictor, so we'll have these 3 choices here. We're still going to pick x1 because it's the lowest sum of squared errors. So x1, sum of squared error, equal to 100. But now, all further models that we choose have to have x1. So the best model we pick for 2 predictors has to have x1 in it. So our only choices are going to be x1 and x2, or x1 and x3. We can't choose x2 and x3. So with those 2 choices, we pick the lower, which is 70. So we'd have x1 and x3. And we get a sum of squared error equal to 70. So now all further models have to have x1 and x3 in them. So we'll just pick model 3. We only have one choice. So we'll include all predictors with a sum of squared error equal to 40. So here's the perks of using forward selection. So we're only going to run 1 plus p times 1 plus p over 2 iterations, which is a lot smaller than 2 to the p as p gets bigger. So here we had 3 possible predictors, so our formula would just be 1 plus 3 times 4 over 2. So we'd end up building 7 models in order to accomplish finding which 4 are best. So just like best subset, after we find our 4, we can either use cross-validation or some statistical technique to find which of the 4 is ultimately the best. The last selection-based method we'll talk about is backward selection. So backward selection works the opposite way of forward and best subset. So instead of starting with the null model, it starts with all the predictors in the model. So for here it would choose x1, x2, and x3. Which just has a sum of squared error of 40. It'll then remove predictors one at a time based off which predicts the lowest sum of squared error. So for our best model with 2 predictors, it can choose from any of these 3. So it would choose sum of squared error equal to 50 or x2 and x3. And then for the model with 1 predictor, it has to drop either x2 or x3. So we can't choose x1 because it's not in our best model with 2 predictors. So our options are x2 or x3, so we would choose x2, which will give a sum of squared error equal to 110. So now we can talk about the pros and cons of each of our 3 choices. So we'll start with best subset. So the pros, it'll check every possible combination. But as we learned, this can be also a con because you can end up with false positive results, or results that seem good, but they're not actually good. They're just positive by chance. And another con is, of course, the runtime. It's 2 to the p iteration, so it'll build 2 to the number of predictors there are in models. So you shouldn't be using this when p is greater than 30. Now, forward selection. So the pros, it's only going to build 1 plus p times 1 plus p over 2 models. So it can be used with a large p. And in fact, it's the only one of the 3 algorithms that can be used when p is large. And the cons are it won't check every possible combination, so there's a chance it might not end up choosing the best model. And then finally, backward selection. So it's going to have the same runtime of 1 plus p times 1 plus p over 2 as forward selection. And it's able to check if different predictors have positive effects on each other. So for instance, if 2 predictors, when they're both added to the model, have an increased advantage in predicting the dependent variable, backward selection is the only algorithm that would be able to sense for this, because it ultimately goes backwards instead of adding predictors one by one. So it can sense when predictors have a positive effect on each other. And then the cons, can't be used when p is big, and it can't be run at all if the number of predictors is greater than the number of observations. Because as we learned, you need more observations than predictors to be able to run linear regression. So, doesn't work with a large P. And just like forward selection, it won't check every combination, so it might not find best model. Now we use the same data, and notice that best subset, forward selection, and backward selection all ended up with different results. So best subset chose X1 if you could only use one predictor, and so did forward selection. But then backward selection chose X2. And then for two predictors, best subset and backward selection agreed, and forward selection disagreed. So by using different selection methods, we're ultimately going to enter different best models, and we'll end up with different results most likely. So the first test statistic we're going to use to compare models is Mallow CP. So here's the results that we got from our best subset. So we had X1 if we were to use one predictor, X2 and 3 if we were to use two predictors, and X1, 2, and 3 if we were to use all three predictors. So the formula for our Mallow CP is going to be the sum of squared error plus the mean squared error of our full model times the number of predictors times 2 divided by the number of observations. So the reason that we can use this test statistic is that as our sum of squared error decreases by adding more predictors, so when we add more predictors, the sum of squared error will decrease. But this part of the equation has P in it, so it will increase. So ultimately, as long as the sum of squared error decreases more than the addition of this part of the equation increases, the Mallow CP will continue to decrease. But if it doesn't, then it will increase. So our goal is to get the smallest, we're going to choose the smallest value possible. So smaller is better. So first we can solve for our null model. So we get a sum of squared error equal to 180 minus the mean squared error of our full model, which is given to us, and then n is given to us. So it's going to be plus mean squared error of full, which is 20, times 0 predictors, times 2, divided by n, and we're going to get a value of 1.8. Then we do the same thing for one predictor. And we get a value of 1.4. And then two predictors, it's going to be 50 for our sum of squared error plus 20 times two predictors times 2 divided by 100, and we'll get a value of 1.3. And then finally, with all three predictors added, and we get a value of 1.6. So notice that when we add predictors, the statistic drops, but when we add all three predictors, it rises. So this means that going from 2 predictors to 3 predictors is not beneficial. And then we're going to choose our lowest value, which is going to be 1.3. So our final model, using best subset and our Mallow CP, is going to be y is equal to our beta 0 plus our beta 2 x2 plus beta 3 x3. So this is the final model we would choose. Now we can do the same thing, but this time we're going to use AIC. So AIC stands for, and hopefully I pronounced it right, Aikaiki Information Criterion. I probably pronounced that wrong, but AIC. So the formula for AIC is just going to be the sum of squared error plus the mean squared error of our full model times P times 2 divided by n times the mean squared error of our full model. So again, our goal is to get the smaller value the better. So we can solve for our null model, which is going to be 180 plus, and then we still have our mean squared error and our n. 0 predictors times 2 over 100 observations times 20, and we'll get a value of 0.09. So we can do the same thing for one predictor, which is our x1. And we'll get a value of 0.07, and then with two predictors, we have a sum squared error of 70 plus 20 times two predictors times 2 over 100 times 20, which gives a value of 0.075. And then finally, with all three predictors, we get a value of 0.08. So we're going to choose whichever one produced the smallest statistic, which is going to be our 0.07 value. So using forward selection and AIC, the final linear regression model we would choose would be y is equal to beta 0 and then plus our beta 1 x1. Now we can do the same thing for our BIC, or Bayesian Information Criterion. So the formula for BIC is just going to be the sum squared error plus the mean squared error of our full model times number of predictors times the natural log of the number of observations divided by n times the mean squared error of our full model. So if we solve for first our null model, 180 plus the mean squared error, which is going to be 20, times 0 times the log of 100, divided by number of observations times 20, and we'll just get a value of 0.09. And we do the same thing for one observation, one predictor, sorry. It's going to be 110 plus 20 times 1 times the log of 100 divided by 100 times 20, and we'll get a value of 0.101, and then two more, so 50 for two predictors plus 20 times 2 times the log of 100, and we'll get 0.117, and then finally with all three predictors we'll do 40 plus 20 times 3 times the log of 100 divided by 100 times 20, and we'll get a value of 0.158. So again, we're just going to choose whichever value is the lowest, which is going to be our 0.09. So with the backward selection and using the BIC statistic, we would simply choose our null model. So y is just going to be equal to beta 0. So that'd be our final model chosen. Okay, so now comparisons. So if you notice the formulas for the Mallow CP and our AIC, so I'll write them out. So sum squared error plus the mean squared error over full times p times 2 divided by n. And then for our AIC, it's going to be sum squared error plus the mean squared error times the full model times p times 2 divided by our n times the mean squared error over a full model. So you notice the only thing that changes here is the denominator. So in both cases, you're ultimately going to end up with the same results, in the fact that the one with the smallest Mallow CP is also going to have the smallest AIC. So the only difference is going to be that the AIC is divided by this extra mean squared error of the full model. Now BIC is going to be different from these two in the fact that BIC more heavily weights added predictors. So generally when you use BIC, you're going to end up with a smaller set than if you were to use AIC or Mallow CP, where you'd probably end up with beta 0 plus beta 1x plus beta 2x2. So by using BIC, you're more likely to drop more predictors. And when you see that, that was ultimately the case when we did it on our backward selection, where all we ended up with was the intercept term. And when we use AIC and CP, we ended up with, here we ended up with one predictor, and here we ended up with two predictors. So BIC, you end up with smaller predictor set in the end, generally. The final statistic we're going to talk about is adjusted R-squared, which shouldn't be confused with regular R-squared. It no longer has the same interpretation of the amount of variance explained. However, our goal is still to achieve a high adjusted R-squared. The better adjusted R-squared, the better the model. So unlike R-squared, adjusted R-squared can be used with models that have different number of parameters. So the formulas for our adjusted R-squared is going to be equal to 1 minus our mean squared error divided by the sample variance of y. So we already learned what the sample variance of y is, which is SST over n minus 1, which is also equal to 1 minus our regular r squared times n minus 1 over n minus p minus 1. So notice that as we add more predictors, we expect our r squared to increase, which will make this value decrease. And then when we add more predictors, this value will ultimately increase. So just like AIC and BIC, by adding more predictors, this value altogether won't necessarily get bigger or smaller. It depends. If you're adding good predictors, it'll get bigger, and if you have bad predictors, it'll get smaller. And then the second part is now we're going to introduce a categorical variable, and we're going to use forward selection. So unlike before, we assumed that all of our predictors added one predictor to our model. But here, ultimately, what the model we have is going to be y is equal to beta 0 plus beta 1 times our age plus beta 2 times summer plus beta 3 times spring, and then plus beta 4 times fall. So that would mean winter is the baseline. So notice that when we add season, we're ending up with an extra 3 coefficient values instead of just 1. So if we're to use forward selection, we're going to choose the highest r squared with one predictor. So our best model that we can choose with one predictor based on r squared is going to be season, which produces an r squared equal to 0.6. And then the next step, our only option is to include both of them, so we just have season and age, which has an r squared equal to 0.8. So now if we're going to judge which of these two models should be our best based on adjusted r squared, we just plug into our formula. So we do 1 minus our r squared value, which is 0.6, and then times n minus 1, so n is 20, and then divided by n minus p minus 1. So notice, since we added season, what our model is going to become is y is equal to beta 0 plus beta 2 times summer plus beta 3 times spring, and then plus beta 4 times fall. So by adding season, we're adding 3 extra predictors. So it's going to be 20 minus 3 minus 1. And this will give an adjusted r squared value of 0.525. And now we can do the same thing for model with 2 predictors, or I should say 2 different variables, season and age. So it's going to be 1 minus 1 minus 0.8 r squared times 20 minus 1 divided by 20. So now it's going to be 4 because age is going to add an extra 1 coefficient minus 1. And it's going to give a value of 0.747. So here's our two choices, 0.525, 0.747. So since we want to choose the larger value, we would choose 0.747. So the final model it would end up taking is the full model, which is just y is equal to beta 0 plus beta 1 age plus beta 2 times summer, beta 3 spring, and beta 4 fall. Okay, so definitely a longer video. So quick review. So resampling methods, they're used because we have limited amount of data and they ultimately help us either improve accuracy or get better estimates of what our true test mean squared error will look like. Feature selection, so significance doesn't work when we have a large number of predictors, so we can either use forward selection, backward selection, or best subset. They each have their own drawbacks. And then once we form models, for each combination of the number of predictors, we can use either adjusted R squared, CP Mallows, AIC, BIC, or cross-validation to ultimately decide which of the models to choose as our final model. And that should wrap up this video. So the practice problems are on Google Forms now, so feel free to check those out. They're more interactive, and I'll be able to see which questions people are getting wrong, I believe, so I can hopefully add more questions for when people are struggling, or add videos for those questions. And other than that, I will see you next time, where we'll be covering the assumptions of linear regression.